All right, so 77, 78. This was taken based on, could we take a sample of something that's not normally distributed and verify that we had a normal or approaching a normal distribution based on getting a certain number. So explain whether or not a normal distribution can be used to model each situation. Explain in a sentence, or a fragment of a sentence is fine. The migration distances of birds is known to be normally distributed with a mean of 3,600 miles and a standard deviation of 350 miles. We wish to know the probability that a random sample of 20 tagged birds will show an average migration over 4,000 miles. So we can indeed deal with this as a normal distribution because they tell us that the migration of birds is normally distributed. Okay, so it doesn't matter that they're only selecting 20 birds. They already told us it was normally distributed, so it's fine to do that. Okay. Number 2 says presence of antibodies in the blood for a certain disease is skewed to the right. So now it's not normally distributed because it's skewed to the right. We randomly sample 60 people to measure the presence of antibodies. We wish to know whether this sample is above or below the average and by how much. So yes, we can go ahead and use this because we have a sample of 60 people. What's the minimum our sample needs to be to show that we approach a normal distribution? What number is half of 60? 30. So we need 30. We need 30 to verify normal distribution. Number 3 says, we wish to know whether a random sample of 20 cars on I-70 at rush hour will show an average speed greater than 50 miles per hour. Characteristics of this population of speeds of cars on I-70 during rush hour are unknown. So we don't know what the overall average speed would be. Can we use this? Is this good or bad? 20 cars. Can we get a normal distribution sample with 20 cars? No, it's not 30. It's less than 30, so it won't work. For the rest of the assignment, read any red flags that might undermine your solutions. Anxiety can often be measured by trained psychologists and can be scaled between 1 and 100. Anxiety as a population parameter is skewed to the right. The mean anxiety level is 30 with standard deviation of 20. Okay, so compute the mean and the standard error. So the mean is given to us being 30. They tell us the standard deviation of this is 20. So if we wanted to find the standard error, we're going to take the standard deviation divided by the square root of n that we're using. So we're going to go 20 over square root 100. So that's 20 over 10. So the standard error would then be 2. So then number 5 says, what is the probability a random sample size of 100 will show a mean anxiety between 28 and 32? So we're going to use our best buddy and pal of the class, the Desmos family. And we're going to see who else just showed up. Oh, Reed. Cool. So we're going to use the mean and standard error. So we're going to go normal distribution. We know that we have a mean of 30 that was given to us originally. We found the standard error to be 2. And then we want to find what's the probability that someone fell between 28 and 32. Oh. Sorry, I didn't have that other projector on. I didn't realize it. So if we were dealing with the new standard error, sample size of 100, what is the probability a random sample size of 100 people will show mean anxiety between 28 and 32? We have about a 68.3% chance of showing this using the standard error in place of the standard deviation. Compute the mean and standard error for a sample size of 25. So then number 6 So we're still going to have a mean of 30. And then our standard error will be the standard deviation that we know is 20 over the square root of 25. So that's 20 over 5. So we'd have a standard error of 4. So it's more spread out the smaller the sample size. Any questions on that first page? Do you feel comfortable with it? Obviously, we're doing standard error quite a bit, so make sure that is going into your sheet that you'll do notes on. This comes, number 7 is part of the same question. We want the sample size to be 25, so that changed our standard error to 4. And now if we go 28 to 32, we can now find that 38.3% of the population would fall within that with the anxiety level that we know. And then the length of films released in Hollywood are known to be normally distributed with a mean of 115 minutes, a standard deviation of 15 minutes. Find the probability that a single film will be longer than 95 minutes. So we can just use our normal distribution on this. We don't have to do standard error because we're just picking one, and we want to know what's the probability that is less than t is less than 95 minutes long. So if you just go and you randomly select, you have about a 9.1% chance that if you had the entire library of movies, you selected one of those movies at random, that the movie would be, the singleton movie would be less than 100 or 95 minutes in length. Find the probability of a random sample of 9 films will show an average time greater than 120 minutes. Okay. So I'm going to just change my standard error. We're going to use square root of 9, which is 3. And then we want to know how many of them have a showing time of these 9 films that's greater than 120 minutes. Infinity. So we have a 15.8% chance that if we select 9 films, incorporated a new standard error of 15 over 3, which is 5, we would have 15.86% chance that our sample of 9 films would be greater than 120 minutes. And then assume the electric bill in Denver is skewed to the right with a mean of 145, standard deviation of 50, so it's skewed to the right. Create a sampling distribution with all 7 positions with a sample size of 16. Okay, so number 10, we have our normal distribution. Woo! We're doing this with the standard error, so we're going to still have this be 145. And then we're going to take our standard deviation of 50 to get our standard error over square root 16. So that's 50 over 4, which is 25 over 2, which is 12.5. So this is plus 12.5. This is plus 25, etc. This is minus 12.5. This is minus 25, so on and so forth. What electric bills are at one standard error above the mean so that one standard error is below the mean? So one standard error above is 145 plus 12.5, so that would come out to 157.5. And then below 145 minus 12.5 is 132.5. And then using the 68, 95, 97 rule, what percent of all random samples of size 16 will produce an average electric bill within one standard deviation of the mean? So you just have to go back to what your normal distribution is. One standard deviation, this distance here would incorporate 68% of our population. And that, my friends, is how you do the homework. Did anyone else show up that I missed? Winter showed up. Let's see. Laura didn't show. Burns didn't show. This not here. Okay, here. Right here. Right here. Did Madeline show? Maddie? No? Maddie, no. Brad's gonna show. Let's see. All right. Good. All right. So I am going to be on 4-5, I believe it is. Or 5-5, excuse me. All right. So I'm on page 11. Okay, proportions, percents, and decimals form can also form normal sampling distributions for large random samples. Before we get to calculations, define. So if you just see P is going to be the percent. Okay, so this will be the population proportion. Okay, and then you have P hat, which is the sample proportion, or sample percent. And then we have U at P, or mu at P is what it, so that's the average mean proportion of all. And then you have phi at P hat. That's going to be the standard deviation of the proportions of all possible random samples. Someone out there is losing it. You hear that coughing? I'm like, dude, stay away from here. All right. What's that? Is there? Example, assume 25% of all people have type O blood. We conduct a random sample of 100 people and obtain their blood pressure, or I guess obtain their blood type, not pressure. 28 people out of 100 in the sample have type O blood. Okay, so we know that our population, what it should be is 25%. Okay, we know that P hat in this case will be the 28 out of 100 because we selected 100 people. So that's 0.28. That should have been 0.25. Okay. Of course, we expect the proportion with type O blood to vary somewhat from sample to sample. These very random samples for a sampling distribution with mu at P hat and standard error phi at P hat formulas are provided without proof. Okay. So they give us that mu at P hat is equal to P. They give us phi at P hat is the square root of P. All right, we stop writing. P minus 1 minus P over N. So in our, if we wanted to figure out what our population is given on the blood type, we know that 25% or 0.25 is type O. So if we apply that to our new given equation, we're going to go 0.25, 1 minus 0.25, and over our sample of 100. And if we just do the calculation on that, we're going to find that this comes out to 0.0433. Okay? So the interpretation of each statistic is simply that a random sample size of 100, we expect to see 25% for type O blood, but will vary by 0.43. So we expect 25% with a plus or minus 4.3%. That'll take place. Can the distribution of a proportion also form a sampling distribution? Yes. However, the central limit theorem tells us that the sample size must be large enough, so we have to make sure that we have n is greater than or equal to 30 if we're sampling, okay, to make it approach a normal distribution. In principle, the three assumptions must be met in order to ensure normal sampling, okay? So for random sampling, you need to have these three things in place. One, random. You have to have some sort of random choosing, okay? Independence. So the probability an individual's response was unaffected by the conditions in which the selection was made. So no outside influence. Okay, and then 3, the sample size is large enough. So in this case, n has to be greater than or equal to 30. Okay, small samples can suffer from a lot of variability. We will actually get into an equation later in the semester that we'll talk about if we have samples less than 30, how do we go about it? And then for the means, the random sample simply has to be 30 or larger to give us a confidence for the sampling distribution to be normal. For proportions, the rule of thumb is a bit different. The sample size, so if we're looking at the sample size, this has to go into account. N times P has to be greater than or equal to 10, and N with 1 minus P has to be greater than or equal to 10. So if we went back and looked at our, if we took our blood example in there, blood type O, we know that we had 25% of what we expect, and that's our p-value. And then our n is our sample size, so we did 100. So in order to make this work, I'd have to go 0.25 times 100. If that's greater than or equal to, well, 0.25 times 100 is 25. So 25 is indeed greater than or equal to 100, so you satisfy it first there, and that has to do with the sample. And then we have to go, well, what about if we do 100 and 1 minus the proportion? Is that also greater than or equal to 10? So we get 100 times 0.75. Is that greater than or equal to 10? Well, I think 75 is greater than or equal to 10, so it satisfies both. So this has to do, this is another test for when you deal with a sample size. That also has to take place, okay? Wowzer, I got done quick. Questions? Again, this is all basing on, can we feel comfortable with the information that we're looking at? There are tests that we have in place to ensure certain things do take place correctly. So I'm going to give you the opportunity to work on page 79 and 80 and get a good start on that. Good. If you came in late after I was done with the homework, if you have the homework done, you can come up and show me.